Hi everyone. So as we had discussed in the previous part, now we are going to provide one of the most commonly used neural networks, which is the convolutional neural network. So the convolutional neural network, the idea behind that is very similar to the regular neural networks, the fully connected neural networks that we have seen so far, with a couple of changes. So again, this neural network is made up of neurons, each with an input and an activation function. Again, we need to learn the weights and biases of these neurons. And we have a loss function at the end, based on which we are trying to perform either a classification or a regression tasks. So the main differentiation now behind the feed-forward neural networks and the convolutional neural networks is that usually we assume that the input of this network is an image. And by having these assumptions, we can kind of simplify the problem that we are trying to solve. So this is an example in this image. This is an example of a convolutional neural network whose input is starting with an image. Then the intermediate layers perform several pixel-wise operations within this image, and then the output layer tries to, in this case, classify between the objects that are seen in this image. So, having said that, let me just provide a brief background on how an image is being represented, although I'm sure most of the people are familiar with that. So in this case, this is a gray level representation of an image. This is what we say only one channel. And what this does is that every pixel of an image has a value between 0 to 225. So this image of a digit 8 here is being represented by a two-dimensional array. The higher the values in each of the corresponding elements of the array, the more dark the corresponding pixel in the image is. So here in this case, as we see in figure 8, we see that most of these values are close to 255. And in regions that correspond to the white space of the image, most of the values are around 0. So this is the case where we have a grayscale image that essentially it's represented by a 2D matrix whose dimensions are the same as the dimensions of the image and whose elements within the matrix range between 0 to 255. Now, if we have a colored image, which is an RGB image, a most common representation of the color image is an RGB image, instead of having only one channel, we have 3 channels. And the concept is the same, but then in each channel we have the red, green, and blue colors that are represented within an image. So we have 3 matrices, each with pixels whose values range between 0 and 255. Now, how this now plays into when this image is an input of a neural network. Let's have, for example, this Einstein image here, in which the dimensionality is 1000 by 1000 pixels. Now, let's assume these 1000 by 1000 pixels, as we have said so far, are represented by a matrix with dimensions 1000 times 1000. Each of the elements of this matrix has a value ranging between 0 and 255. Now, if we were to connect all these pictures through a fully connected neural network that we have seen so far, what would happen is that each of the hidden layers of the network would be connected with all of these pictures. Now, there is a big problem with that, and the main problem is that usually the images are of high dimensionality, are signals of high dimensionality. So if we are to connect each node with all the input pixels, then we would have to learn a very high number of parameters. So for example, let's say that if this image goes through 1 million hidden units, then what we would have to learn is 10 to the 12 number of parameters. So the question is, can we do better? The answer is yes, and we are leveraging several properties within the image in order to reduce the number of parameters that can be learned from this image. So the first property that we are leveraging is the idea of convolution. Now, what this means is that within an image, usually local components within an image have a very useful information. So instead of finding associations between components within an image that are far away, let's say this picture on the left and this pixel upper right, what we are only trying to see is operations that are local within pixels that are neighbors within an image. So by doing that, we can reduce the number of parameters that need to be learned from this convolutional neural network from 10 to the 12 to 10 of the 8. And this is also motivated by an extensive amount of research in computer vision, in which researchers tend to first take pixel-wise combinations within an image in order to actually provide a meaningful feature space. And this is being taken from the ideas of convolution. So beyond the idea of convolution, the second important thing is the idea of stationarity. And what this means is that usually we assume that if we have a filter in this small area of the image, because images tend to have stationary information between neighboring pixels, we are going to have a common information within the pixels that are close by to this area of the image. So instead of having different filters, different weights for all these regions within this block, we can have a weight sharing, as we say, which is the fact that within this block we assume that we have the same weights that are being used in order to transform the pixels in this block. And then the third way, the third novelty is the fact that now that we have taken information from local pictures within the image, we need to actually take a more higher level information from that image in order to make sure that we can capture a more general representation that might actually depict the objects that are within this image. So that's the idea of max pooling. After we have taken transformations from the local pictures of the image, we summarize those transformations through a max or an average filter in order to take a reduced transformation of these filters. So these were the main ideas, the three main ideas, based on which convolutional neural networks are being built. So what we are going to see is that how these three main ideas play out through actually building these convolutional neural networks. And by that, we start with the idea of convolution. So the idea of convolution is an idea that comes from the signal processing, in which we have an original image, and we are passed this original image, in this case this is just a 3x3 input, through a kernel, through a filter as we say, from which we get an output. So this is the definition of the two-dimensional convolution. In this definition, what this says is nothing but we are performing pixel-wise multiplications between this input image and shifted versions over x and y of that kernel. And after performing these multiplications between the input and shifted versions of the kernel in the xy domain, we sum that and then we get a final output for each kernel. So let me actually demonstrate that through an example. So in this example here that we have, what we have is the same input of an image. We have this kernel, and then we are trying to get this output, which results from the convolution. So how does the convolution works is that, for example, when the shift of this kernel is at 0, 0, meaning this kernel is not shifted at all, by convention, we assume that the central element of the kernel is in the beginning of the image. So essentially, having placed the central element of the kernel in the beginning of the image, now we see how much overlap the kernel has with the actual image. And we see that this overlap is only these 4 pixels. Then we compute the multiplication of each of these pixels within the image and the kernel. And in this case, we have 0 times 1, 0 times 2, 0 times 0, 1 times 0, and so forth, and all these things. So in this case, we have 0 plus 0 plus minus 8 plus minus 6. And the sum of all these is minus 13. Now the sum of all this, which is minus 13, is assigned to the 0, 0 location of the output image. So this was the result by actually not having shifted the kernel at all. The kernel was at 0, 0. And here is the fact that the kernel was at 0, 0 from the shift of the h function. Now let's say that we want to shift this kernel by one pixel to the right. How will this work? Is that we will have the output, which is at 1, 0. We will have shifted this kernel once by 1 pixel to the right, and then the corresponding figure is going to be reflected like that. So that resulted by shifting this to the right. Now, again, we see the overlap between the actual image and the kernel. The overlap is these 6 pixels. We take the multiplication of the element-wise multiplication of each of these 6 pixels that are overlapping, and then we sum the results from this multiplication, and then the sum is minus 20. So then this output is assigned to the output 1, 0 of the resulting image. So we see that this minus 20 is assigned to this first row and second column of the image. And the same thing goes now when we would like to shift the kernel 2 pixels to the right. So when we are shifting this kernel 2 pixels to the right, this is what we get. And we do the same exactly operations. So this output minus 17 is now assigned to the pixel 2 times 0. Now, when we want to shift the kernel 1 pixel down, what happens is that we get images that look like that. And by doing that, then we get the output of the image that it is at 0, 1 instead of 1, 0, because we have shifted 1 pixel on the y-axis. So this 0, 1 is the output minus 18, and it is assigned here. Now the same way goes when we want a shift of 1 down, 1 right, and 1 down, and so forth and so on. So in this example, in this link here, I encourage you to take a look at this link, which is also on the slide. We can see how we can perform a convolution operation between a two-dimensional out input with a two-dimensional kernel, and in this case the dimensionality is 3 times 3. So what do these convolutions mean in practice? Let me try to explain what these convolutions mean in practice by actually starting on trying to understand how this convolution, this very simple convolution that we saw with images and kernels of size 3 times 3, can be expanded to images. So in the case of a real image, what we most probably have is a kernel of size 3 times 3 or 5 times 5, and then an input image of size 512 by 512, or so, and so forth and so on. So what happens is that this input kernel, this kernel, is being passed through each element of the input image, and then by having this convolution operation, we can have an output of the image from this kernel. So this is an example of how this is performed. This is an example of the kernel, this is an example of the input image, and this is an example of the output. So if this kernel is what we call an identity kernel, and this is the input of the image, then the identity kernel does nothing but having as the output the same pixels within an image. On the other side, if we have this kernel, what it does is that it assigns within its neighborhood that is being applied, it assigns all pixels to 0, but the pixel on the middle left corner. So what it does is that it will assign every time whatever pixel we have to the pixel on the left. So this kernel represents one shift left. Now let's say that we have another type of kernel that looks like that. So what this type of kernel does, again within each neighborhood, it takes the sum of all pixels and it divides the sum of all pixels by 9. And then it assigns this divided value to each pixel of the output image. So what does this result? This results essentially in a blurred image. This is what we call a median filter, and we usually use it when we would like to smoothen out our input. Either this is an image or either this is a one-dimensional signal. Now, if we combine what we have learned so far, so if we have a kernel who is an identity kernel multiplied by 2, if this is subtracted by the mean filtering kernel, what we can have is actually a filter that sharpens the edges of the image. And this is how this sharpening operation would look like. So this is an example of how this sharpening operation would look like if we have this entire Einstein image and then the edges of the image are being sharpened. So traditionally in computer vision, what has been happening is that these kernel operations, so the weights of these kernels and where these kernels are going to be 0 or more than 0 or not equal to 0, are being decided manually through a person who kind of has the intuition and says, okay, now in order to fulfill this task, I need to blur the image or I need to sharpen my image. Now, what convolutional neural networks do is that instead of having this human-driven knowledge, they learn the weights of these kernels based on the data and based on the output of interest. So let's go and start to see this idea. So for example, this could be an input of a convolutional neural network. This is nothing but the inputs of one image that are flattened in the 1D space. So in this case, what we have is that in this we have one input, we have one hidden layer, and in this image we see the two first properties that we discussed. The first property is the property of convolution or the property of locality. So what we see is that each of the hidden layers is not connected with all the inputs of the image, but it's only connected with two inputs. And the second property that we see is the property of stationarity. So these inputs are not connected together with different weights, but all weights W1 and W2 are the same within each input because the property of stationarity is being leveraged. So this is an example when we say that we have a 1D convolution. We only use one type of filter with parameters W1 and W2. The filter size that we are using is a filter size of 2 because it has two parameters. And the stride that we are using is a stride of 2. And by that we mean that after having these two inputs led to the first hidden layer, these two inputs are not seen again by any hidden layer, and we go to the next two inputs. Now, if we would want to have an overlap among these, what we could have is that we could decrease the stride by 1. So instead of having an overlap 0, we would have an overlap 1. So in this case, these two inputs are guided to the first hidden layer, but then the second input combined with the third is also guided to the second hidden layer. So there is an overlap between this second input to the first and to the second hidden layer as well. So this was the example when we have a 1D convolution. What happens when we have an input that is essentially 2D? we can have exactly the same thing. So instead of having this one-dimensional input, we can actually have inputs that are like that, and where these local parts of this two-dimensional input are being led to this smaller output that has resulted from a 2D convolution of this input. Now we can see here that this output is not 2D, but it is 3D. And why it is 3D? Because not only one filter is being learned for each region, but multiple features are being learned from this region. These filters can be, for example, filters like median, smoothing, sharpening, but the point is that all the parameters of these filters are not being pre-identified, but they are being learned from the data that we have. So this could be an example of a grayscale image in which we only have one matrix. This here on the right could be an example of an actual RGB color image in which we have three input matrices, and we perform exactly the same thing over each channel, exactly the same operations over each channel. Now, having said that, there are several parameters that can be actually pre-identified, predetermined when we do this 2D convolution. The first parameter is the depth. So by depth, we mean the number of filters that we are going to use for the convolution operation. If you remember here, we said that instead of using only one filter for each input region, we can use multiple filters. Now, the other input is the stride, which means what would be the overlap? What would be the overlap between neighboring pixels within an image, based on which we will perform the filtering operation. And finally, another parameter that can be also predetermined is the zero padding, and by zero padding is nothing but how many zeros are we going to have in the border, around the border of the image, so that we can take care the bordering pixels of an image. Now, what we have said so far is that the convolution operation essentially takes care of two things. It takes care of the locality by actually computing local filters within regions of an image, and it takes care of stationarity as well by actually computing the same local filters within multiple neighboring regions of the image. Now, what we haven't said so far is how the property of max pooling, the property of we would like to find higher level representations within an image, is going to be addressed. So for that, what we are doing is that we are doing what we call a max pooling operation or a spatial pooling operation. So this means that after we have performed these filtering operations within the image, we are taking these filtering operations and we are computing maximum, minimum, or other statistics within these local regions of the image. So this is what we call spatial pooling operation, and one very common thing to perform is actually a max pooling operation. So in this case, if the filtering of this image had resulted in a dimensionality of 8 times 8, if we perform a max pooling with 2 times 2 filters and stride of 2, which means that we won't have an overlap, what will happen is that every 2 by 2 pixels, we will actually get an output which is the maximum value of these 2 by 2 pixels. And the main benefit of this is that essentially it's going to reduce the dimensionality of the input space by a significant amount. So after that, this input space has to be the input of another set of a convolution operation and another set of max pooling operation in order to provide further dimensionality reduction. And this is an example of how this would look like. So after having an original image, after having an original image, we can have these convolutional operations followed by max pooling operations, and then successive convolution and max pooling operations. Now, how these operations are going to be summarized in order to provide a final output for the image, this is where fully connected layers come in. So after we have all these partial convolutional and pooling operations, we are going to actually take this last pooling layer and pass it through fully connected layers. And by these fully connected layers, we can get further higher level representations of the input image that gradually lead us to the final output. So how this would work in practice is that if we have this image of a car here, let's say that we have several convolutional and max pooling operations here, and then these are followed by some fully connected layers. So the last output of these fully connected layers is going to be essentially a likelihood function, which provides the likelihood of having each of these objects within an image. We can see from this picture here that essentially the first layers of this convolutional neural network kind of represent edges within an image, while the last layers, as we understand, what they have done is that they have kind of localized the region of the car within an image. So this is essentially what we're saying, that the first layers capture more lower level representation, such as the edges, while the last layers can capture more higher level representations, such as the objects. This is another example of how this can play out with numbers. We have this initial input, which is a number 8, an image of the number 8. This input goes through convolution and max pooling layers, and then it goes through two fully connected layers to provide a final output. So we see here the activations of the fully connected layers, and we see that the final output essentially, in this final output layer, only the number 8 is being actually activated and provides a higher likelihood for the corresponding input. So, to summarize, what we have seen so far is that in this convolutional neural network, the first layers of the network perform the convolutional operations based on which local pixels within an image are being transformed through filtering operations to provide an output of these filters. Then these filtering operations are being transformed to reduce in dimensionality through max pooling layers, and these are being successively performed multiple times in order to result in lower dimensional feature spaces. After that, the last layer of the max pooling operation is being flattened and is being driven through several fully connected layers in order to further provide higher level representations of the input space. After having done that, in the final layer, which is in this case, for example, the classification layer, it could also be the regression layer, and in this one, we actually make a decision for the corresponding input. So what are several parameters that can be actually tuned while having these neural networks? We have a set of interesting hyperparameters here. One hyperparameter is the learning rate. So the learning rate is essentially how much we will update the weight during optimization. It's the same thing that we have seen in gradient descent and the same thing that we have seen in backpropagation. Another important parameter is the number of epochs. So what happens usually is that one epoch going through this iterative operation once does not really provide any significant results because it doesn't make sense to just update the weight once. So the number of times these weights are being updated is called number of epochs. Another important parameter, especially when we have a very large data in our input space, is the batch size. So instead of passing the entire data samples in the neural network in order to train the corresponding weights, we can pass subsets or batches, as we say, of these samples. The number of smaller batches that are being passed through the neural network to perform training is called batch size. Of course, there are several other hyperparameters, such as the activation function that we have seen so far as well, the number of hidden layers, the number of units, the dimensionality of the filter, the stride size, the initialization of the weight. So, for example, a uniform distribution can be used to initialize the weights, as well as the dropout. So the dropout is essentially how many of these weights we're going to drop, how many of these neuron connections we're going to drop. And usually the dropout is a very important parameter in order to have a good trade-off between efficient training and precision. So how are we going to actually understand and find which are the best parameters, which are the optimal parameters for our problem? Through hyperparameter tuning in a validation set, by performing a grid or a randomized search, since in this case the initial set of parameters is quite a lot. So what we have learned so far about deep neural networks, we have learned that essentially deep neural networks can provide us richer representations of the input space. Instead of having handmade features for these deep neural networks, we can actually have features that the network learns by itself. One example like that is the fact that the network learns the filters that are being implemented on an image from the data of interest, rather than predefining the filters that are going to be operated on the image. We have seen several challenges instead of training, in terms of training the neural networks. One challenge was the fact that we have a lot of data and that we have essentially a very big number of parameters that need to be stored and trained. Pre-training these parameters by using unsupervised methods such as the deep belief networks and the autoencoders can actually boost the performance of the corresponding systems. And we have also seen a very important neural network, one of the most frequently used neural networks, which is the convolutional neural network. Usually this network is being performed in order to classify or make some type of regression for images. And we have seen that this neural network essentially takes advantage of three key operations that are being performed in images. One is the convolution operation, meaning that local image properties actually matter in order to understand the content of an image. The next property is the stationarity operation, meaning that pixels within a neighborhood of an image tend to have similar distributions, and this is being taken into account through weight sharing. And then the third property is the fact that by having these low-level representations, we would like to actually combine these low-level representations into a more higher-level representation in order to make the final decision for the input. And this higher level representation of the image can be performed through max pooling operations that increase the robustness and also benefit the compression of the input space in order to actually reach the output of interest. So this wraps up the class on deep neural networks, and I'll see you all next week to provide more examples and to discuss more questions. In the meantime, please feel free to ask your questions on Piazza, and see you soon.